Imagine you are standing inside a room the size of a small school bus, surrounded by gold-coloured insulation and copper wiring, and the world outside your window is moving at 123,000 kilometers per hour. The planet you are falling into is 764 times larger than the one you were born on. Its clouds are ammonia and water and ice, layered in bands of ochre and ivory that stretch for tens of thousands of kilometers in either direction. You were not slowing down. You were never meant to. What did that spacecraft feel in those last 91 seconds? And more to the point, what did it find? Here is what we are not going to do in this video. We are not going to talk about Cassini as though its death was the story. The death was not the story. The death was the price you pay to get the story. What Cassini revealed in those final dives, in the gap between Saturn and its rings, in the atmosphere it sampled breath by impossible breath, in the magnetic field data that still keeps planetary scientists awake at night. That is something far more extraordinary, far more unsettling, and far more consequential than the farewell ceremony it received on September 15th, 2017. Three things. Three revelations from those last months of flight that I want to put in front of you today. The first will change how you see the most recognizable planet in the solar system. The second will destabilize one of the foundational principles of how planets work. And the third one, I'll be honest, I had to sit with for a long time before I could properly write about it. The third suggests that right now, tonight inside our solar system, the conditions for life may be operating in a body of water the size of Earth's oceans, completely hidden beneath a shell of ice, in the orbit of a planet we have been looking at since Galileo pointed a handmade telescope at the sky in 1610. We know less about what that means than we would like to admit. And that, to my mind, is where the real story begins. On the morning of October 15th, 1997, a Titan IVB Centaur rocket stood on Launch Complex 40 at Cape Canaveral Air Force Station, loaded with a spacecraft that represented the combined intellectual labour of 17 nations, roughly 5,000 engineers and scientists, and a total cost that would eventually reach $3.9 billion. The rocket itself was not the most elegant object humanity had ever constructed, but strapped inside its payload fairing, enclosed in gold foil thermal blankets, and held together with more than 22,000 wire connections, was a machine that its builders genuinely believed might answer one of the oldest questions in planetary science. What, precisely, is Saturn? Not what it looks like. We had known what it looked like since 1610. What it actually is, at its core, in its storms, in its rings, in the impossible chemistry of its moons. That was what Cassini was built to determine. The spacecraft was named after Giovanni Domenico Cassini, the 17th century Italian-French astronomer who discovered the gap in Saturn's ring system that still bears his name. The gap, the Cassini division, sits between the A ring and the B ring, a dark band of relative emptiness roughly 4,800 kilometers wide, caused by the gravitational resonance of Saturn's moon Mimas. In 1675, Cassini saw this division through his telescope at the Paris Observatory. 322 years later, a spacecraft named in his honour was launched to fly directly through the region he had first described. There is a poetry to that sequence of events that I find genuinely moving, in the way that only science, with its long patience, can be moving, but the story almost ended before it began. In the mid-1990s, as the spacecraft was being assembled and tested, a protest movement developed in the United States around the question of its power source. Cassini was not solar-powered. At Saturn's distance from the Sun, an average of 1.43 billion kilometres, roughly 6 times the Earth-Sun distance, solar panels are simply not viable. The sunlight arriving at Saturn is about 100 times weaker than what Earth receives. You cannot run the scientific instruments, the transmitters, the heaters that keep the electronics from freezing on that kind of diluted starlight. So Cassini was nuclear-powered, carrying 32.7 kilograms of plutonium-238 dioxide in 3 radioisotope thermoelectric generators. The decay heat from the plutonium converted directly into electricity through a bank of thermocouples. The protest groups argued that if the rocket exploded on launch, or if the spacecraft's trajectory required a close flyby of Earth for a gravitational assist, which it did in August 1999, the dispersal of plutonium over populated areas could cause a public health catastrophe. NASA and its partners responded with extensive documentation of the safety testing. The fuel pellets were ceramic encased, designed to survive re-entry, impact and explosive overpressure without dispersal. The probability of a catastrophic release was calculated at less than 1 in a million. The launch went ahead. I am not going to tell you the protesters were foolish. Risk assessment is genuinely difficult, and the history of rocket failures is sobering. But I will say this: had Cassini been stopped, had a court injunction or a political decision kept it on the ground that October, the discoveries we are going to discuss in this video would not exist. The implications of what Cassini found at Enceladus alone, the subsurface ocean, the hydrothermal vents, the molecular hydrogen, represent arguably the most significant indication of potential extraterrestrial habitability ever detected from any spacecraft at any planetary body. The cost-benefit calculation, viewed from here in 2026, looks very different than it did from the parking lot outside Cape Canaveral in October 1997. The spacecraft launched at 04:43 UTC. Its Titan IVB Centaur upper stage carried it to an initial velocity of about 3.2 km per second before the onboard engine burns took over. Cassini could not simply point itself at Saturn and ignite its main engine. The physics of solar system navigation do not permit that kind of brute force. To reach Saturn in a reasonable time frame, meaning within roughly 7 years rather than the decades a purely direct trajectory would require, Cassini needed to use the gravity wells of other planets as a series of slingshots, gaining kinetic energy with each close pass. This trajectory, known as the Venus-Venus-Earth-Jupiter Gravity Assist Maneuver, or VVEJ, would take the spacecraft on a looping path across the inner solar system before finally hurling it outward toward the outer planets. First, 2 flybys of Venus, separated by just over a year. April 26, 1998 and June 24, 1999. Each pass within 600 kilometers of Venus's cloud tops, skimming through the outer wisps of its dense atmosphere, gaining velocity from the planet's gravity. Then back toward Earth for the flyby on August 18, 1999, passing within 1,171 kilometers of Earth's surface, close enough that people in rural areas of Eastern Europe might, in theory, have looked up and seen a bright point of reflected sunlight crossing the sky. From Earth, the spacecraft picked up an additional 5.5 kilometers per second of velocity, and then, in an outward trajectory that swept past the asteroid belt, to Jupiter on December 30th, 2000, passing within 7 million kilometers of the giant planet for one final gravity assist that pushed Cassini's total speed high enough to reach Saturn. 7 years, 3,500,000,000 kilometers, a trajectory that curved in and out and back again, threading between gravitational fields with the precision of a billiard shot executed in 3 dimensions by a machine travelling faster than any human-made bullet. On June 30th, 2004, Cassini fired its main engine for 96 minutes, slowing itself into Saturn orbit. The burn had to work perfectly. Saturn Orbit Insertion, SOI, was a single-shot maneuver. If the engine failed to ignite, the spacecraft would fly past Saturn and disappear into the outer solar system. If the burn was too short or too long, the resulting orbit would be incorrect. The engineers had planned for every contingency they could conceive of, and then they waited, in JPL's mission control in Pasadena, California, through a communications delay of 84 minutes, the time it takes light, and thus radio signals, to travel from Saturn to Earth. The burn succeeded. Cassini entered Saturn orbit and, in doing so, became one of the most accomplished deep space explorers in the history of human civilization. What it would find over the next 13 years would outpace almost every prediction its builders had made. And what it would find in its final 5 months, the grand finale, the 22 dives through the gap between the rings and the planet, and the last 91 seconds of atmospheric entry would raise questions that are, as of today, still unresolved in the peer-reviewed literature. But before we get to the final seconds, we need to understand what Saturn is, because Saturn, it turns out, is not what anyone thought it was, and it took a spacecraft built by 5,000 people and launched on a nuclear-powered rocket at 04:43 UTC on a Thursday morning in 1997 to begin showing us what it actually is. Saturn is the sixth planet from the Sun. It orbits at an average distance of 1.43 billion kilometers, taking 29.4 Earth years to complete a single revolution. It is a gas giant, roughly 95 times the mass of Earth, though its density is so low, lower than liquid water. The famous fact that it would float in a bathtub of sufficient size, that its volume is largely empty space and extremely tenuous gas. It rotates rapidly, completing one day in approximately 10.5 Earth hours, a spin rate fast enough to visibly flatten it at the poles. Saturn's equatorial diameter is 120,536 kilometers, while its polar diameter is only 108,728 kilometers, a difference of nearly 12,000 kilometers that gives it a distinctly oblate appearance even in a backyard telescope. The rings, the defining visual feature, the reason it appears in every child's astronomy book and every representation of outer space, are a disk of ice and rock fragments extending outward from roughly 7,000 kilometers above the cloud tops to a distance of more than 280,000 kilometers, but compressed into a vertical thickness, in the main rings, of only 10 to 30 meters. That is not a misprint. An object with a horizontal extent comparable to the distance between the Earth and the Moon is, in many places, no thicker than a 3-story building. The ring system's ratio of width to thickness is more extreme, proportionally, than a sheet of paper. What holds the rings together? What created them? How old are they? These were among the primary questions Cassini was sent to answer, and the answers, when they finally came, were not what anyone had prepared for. Here is a question that sounds so ordinary it barely registers. How old are Saturn's rings? You might assume we had answered this long before Cassini arrived. After all, astronomers had been studying Saturn's rings since 1610. The Voyager 1 and Voyager 2 spacecraft flew past Saturn in 1980 and 1981, returning extraordinary imagery and data. Surely, in 4 centuries of observation, someone had pinned down the origin and age of the most recognizable structure in the solar system. They had not, and the reason they had not is one of the more elegant traps that planetary science has ever stumbled into. The rings of Saturn looked ancient. They looked like something that had been there from the beginning, a primordial accretion disk left over from Saturn's formation 4.5 billion years ago, preserved by the planet's enormous gravitational influence and its distance from the rocky, collision-prone inner solar system. The rings were made of water ice, extremely pure water ice, as reflective as fresh powder snow, which is itself a clue. And the general assumption was that they were a relic of the early solar system, perhaps the remnant of a moon or a comet that strayed too close and was gravitationally shredded. But there was a problem hiding inside that assumption. 2 problems, actually, and they had been staring at scientists for decades without being taken quite seriously enough. The first problem was contamination. Ring material, being composed primarily of water ice, is inherently reflective, but space is not clean. The outer solar system is traversed by dust grains from comets, micrometeorites from the asteroid belt, and charged particles from the solar wind. All of this material tends to darken surfaces over time, icy bodies that have been exposed to the space environment for billions of years. The moons of Uranus, the surfaces of Kuiper belt objects, the older regions of the Jovian moons, are typically dark grey or brownish, their original ice buried under a thick coating of carbonaceous material. Saturn's rings, by contrast, were spectacularly bright. Too bright, if they were really 4.5 billion years old. The contamination rate from interplanetary dust should have darkened them significantly. If they were really ancient, something would have had to be continuously refreshing the ring material, cleaning off the dark layer somehow, which is possible, but would require an implausibly active and sustained process. The second problem was mass. To estimate the age of the rings, you need to know how much mass they contain. More mass means more material is available to dilute the incoming contamination. A very massive ring system can absorb dark dust for a long time before its overall reflectivity drops measurably. A less massive ring system would darken faster. But measuring the total mass of Saturn's rings from a distance is genuinely difficult. You can study how the rings gravitationally influence passing moons and small moonlets embedded within them. You can model the ring's structure using stellar occultation data, watching how the rings block the light of background stars. But all of these methods are indirect, and they carry substantial uncertainty. Before Cassini's grand finale, the estimates of Saturn's ring mass had a wide error bar, wide enough that the rings could be either ancient or relatively young, depending on which estimate you accepted. The conclusive answer, required getting close, really close. Close enough to feel the gravitational pull of the rings directly, to let the planet's own gravity sing its secrets into the spacecraft's accelerometers and transponders. That is exactly what the grand finale was designed to do. In April 2017, after 13 years in Saturn orbit, after 293 orbits of the planet, after 162 targeted flybys of Saturn's moons, Cassini began its final chapter. A flyby of Titan on April 22nd used that moon's gravity to reshape Cassini's trajectory, sending the spacecraft vaulting over the outer edge of the ring system and into an entirely new class of orbit, one that passed between the rings and the planet. Each orbit took approximately 1 week. Each pass brought the spacecraft through the 2,000-kilometer gap between Saturn's innermost ring and the top of its visible atmosphere, at an altitude ranging from 1,600 to 4,000 kilometers above the clouds. For the first time in the history of space exploration, something was actually inside Saturn's ring system, not outside it, not flying tangentially past it, but threading directly through the gap, sampling the material there, measuring the gravitational field from a proximity that had been impossible in any previous orbit. And the gravity data that came back from those passes did something extraordinary. They told the team the mass of the rings. The result was stunning. The rings were light, far lighter than the models that favoured ancient origin had predicted. The mass of the entire main ring system, the A ring, the B ring, the C ring, the Cassini division itself, came to approximately 15,400 times the mass of Saturn's small inner moon Mimas, which is itself only about 3.7 times 10 Focht kilograms. In total, the rings contain about 15.4 Mies masses, or roughly the equivalent of a ball of ice 160 kilometers in diameter. For context, this means the rings are significantly less massive than some of Saturn's smaller moons, despite spanning a horizontal distance comparable to the Earth-Moon distance, a ring system that light could not have survived for 4.5 billion years in the current space environment without darkening catastrophically. The contamination analysis was decisive. If the ring mass was really this low, the ring material would have darkened to a grey-brown state long ago, unless the rings were not 4.5 billion years old, unless they were new in geological and planetary terms means something rather different than new in human terms. The analysis placed the formation of Saturn's main rings somewhere between 10 million and 100 million years ago. Most researchers working on this problem have converged on a figure towards the younger end of that range. Perhaps 40 to 50 million years old, with a significant fraction of the work pointing at around 100 million years as an outer bound. Either way, when Saturn's rings formed, dinosaurs were already walking on Earth. The Cretaceous period was underway. Tyrannosaurus rex was perhaps 30 million years in the future. Let that sink in for a moment. The most famous feature in the solar system, the rings that generations of children have gasped at through telescopes, that appear in every depiction of outer space from science fiction to serious astronomy. Those rings did not exist for most of the solar system's history. Saturn was, for 4.4 billion years out of its 4.5 billion year life, an unringed planet. You could have looked at it through Galileo's telescope 400 million years ago and seen a featureless oblate sphere, no different at first glance from Jupiter. We happen to arrive, in our brief, flickering moment of civilization, at precisely the time when the rings exist. We are, as James O'Donoghue of NASA Goddard put it, lucky to be around to see them. We are also lucky that Cassini, by diving between them and the planet in its final months, gave us the gravity measurements needed to reach this conclusion. Without the grand finale orbits, the mass of the rings would still be debated, and the rings' age would remain uncertain. Without the age, the entire question of their origin, what shredded or coagulated to form them, what event in the solar system's relatively recent history created one of its most spectacular structures, would remain permanently opaque. But here is where the first loop opens wide, because knowing the rings are young does not close the question. It opens three new ones. What created them? What was shredded or what collided to produce 160 kilometers worth of nearly pure water ice distributed across a disk hundreds of thousands of kilometers wide? Where did the ice come from? A lost moon, a captured Kuiper Belt object, a cometary impact on a pre-existing but smaller ring system? And what does the youth of the rings tell us about the dynamics of Saturn's moons, which are themselves subject to tidal forces that are measurably pushing them outward from the planet even now? These are questions that the grand finale raised while simultaneously closing others, and they are questions that no subsequent mission has yet been designed to answer with sufficient precision. Which means that as of today, in 2026, we know the rings are young. We do not definitively know why. That tension between the closed answer and the opened question is going to be the recurring motif of everything that follows, because every single discovery that Cassini made in its final months followed the same pattern, a resolution that contained, buried inside it, a deeper mystery, and no mystery cut deeper than what the spacecraft found when it looked at Saturn's magnetic field. Let me describe a rule of planetary physics that has held, without exception, for every planet with a magnetic field ever measured by any instrument anywhere in the solar system. A planetary magnetic field is generated by a process called magnetohydrodynamic dynamo action. The basic principle is this: a conducting fluid, liquid iron in the case of Earth, liquid metallic hydrogen in the case of gas giants, circulates inside the planet, driven by heat convection and the planet's own rotation. The movement of this electrically conducting fluid through a pre-existing seed magnetic field generates electrical currents, which in turn amplify and sustain the magnetic field. It is a self-reinforcing loop, a kind of electromagnetic bootstrap, and it requires three things: a conducting fluid, a source of heat to drive convection and rotation. But there is a subtler requirement, less often discussed but just as essential. The fluid circulation cannot be perfectly symmetric around the rotation axis. If the convection patterns were perfectly organised around the spin axis, if the fluid were circulating in perfectly ordered tubes aligned with the planet's rotation, the dynamo would not work. A perfectly symmetric dynamo is a dead dynamo. You need some asymmetry, some wobble, some chaos in the circulation to break the symmetry and allow the magnetic field to grow and sustain itself. What this means in practice is that every planetary magnetic field we have ever measured is tilted. Earth's magnetic field is tilted approximately 11.3 degrees relative to Earth's rotation axis. Jupiter's is tilted about 6 degrees. Uranus's is tilted nearly 60 degrees. Neptune's is tilted 47 degrees. Mercury's small magnetic field has a tilt of about 14 degrees. Even the Sun's polar magnetic field is somewhat tilted relative to the solar rotation axis. Every single magnetic field, every single measurement, a consistent, universal offset between the magnetic axis and the rotation axis caused by the fundamental physics of how dynamos work. Then Cassini measured Saturn's magnetic field. The first hint that something was wrong came from the Voyager flybys in 1980 and 1981. Voyager's instruments measured Saturn's magnetic field and found it extraordinarily well aligned with the rotation axis, suspiciously well aligned. But the Voyager measurements were made from a distance from outside the ring system, and the precision available was limited. The alignment looked very nearly perfect, but the uncertainties in the Voyager data left open the possibility that there was a small tilt, perhaps a degree or two, that the instruments simply were not sensitive enough to detect. Cassini, in its early and middle mission phases, measured the field with considerably better precision from a variety of distances and orbital orientations. The measurements kept coming back the same way. The tilt was smaller than Voyager had suggested, much smaller. Cassini's magnetometer team, led by Professor Michael Doherty of Imperial College London, watched the numbers with growing unease as orbit followed orbit, and the tilt refused to grow large enough to be explained by standard dynamo theory. But it was not until the grand finale passes, flying through the gap between the rings and the planet, at closer range than any magnetometer had ever operated around Saturn, in a region free of the confounding magnetic signatures of the ring plasma, that the full picture became clear. The magnetic tilt of Saturn is less than 0.0095 degrees. To put that in physical terms, Earth's magnetic axis is offset from its geographic pole by about 11.3 degrees, which is roughly the angular distance between London and Cairo as seen from Earth's centre. Saturn's magnetic axis is offset from its geographic pole by less than 1/100th of a degree, an offset so small that it cannot currently be distinguished from zero by the most sensitive instruments humanity has ever flown to the outer solar system. This should not be possible. According to every theoretical framework for how planetary dynamos work, frameworks that have been validated against Earth, against Jupiter, against Uranus, against Neptune, against even the tiny remnant fields of ancient Mars and Mercury, a dynamo aligned this precisely with its rotation axis cannot sustain itself. The symmetry would prevent it. The field should collapse or oscillate or drift. But it doesn't. Saturn's field is there, it is strong, comparable in absolute terms to Earth's surface field, and it is aligned. When Doherty's team published their grand finale magnetometer results in the journal Science in October 2018, the paper was careful and precise in its language, as all good scientific papers are, but the conclusion that Saturn's tilt was below 0.0095 degrees, tighter than any previous measurement, tighter than any planetary dynamo theory could comfortably account for, landed in the planetary science community like a slow-moving thunderbolt. The debate that followed was intense, and, to be honest, it is still ongoing. Several explanations have been proposed, and they divide into two broad categories. The first category suggests that Saturn's dynamo is not actually symmetric. There is a real tilt, perhaps at a level of 0, 1 degrees or smaller, but something inside the planet is obscuring it from our measurements. The most developed version of this idea involves a layer of stably stratified, slowly rotating fluid just above the dynamo proper, perhaps a region where helium is raining out of solution from liquid hydrogen, a process called helium demixing that is thought to be occurring inside Saturn. And this stratified layer could act as a filter, smoothing out the magnetic field before it exits the planet, selectively removing the tilt component and leaving only the symmetric part. This explanation is elegant. It is physically plausible. It makes testable predictions, particularly that if you could somehow see deeper into Saturn's interior, past the filter layer, you would find a tilted dynamo underneath. But it creates a new problem. The filter has to be tuned with extraordinary precision to reduce the tilt from whatever value it has at the dynamo level to less than 0.0095 degrees at the surface. Even a small imperfection in the filtering would leave a detectable residual tilt. Why is Saturn's filter so perfect? The second category of explanations is more radical. Perhaps our understanding of dynamo theory is incomplete, and there are conditions, specific combinations of internal structure, rotation rate and fluid properties, under which a nearly perfectly aligned dynamo can persist. This would require a significant revision of the theoretical framework, not just a small adjustment. What the grand finale measurements established, beyond any doubt, is that Saturn's magnetic field represents an anomaly that breaks the established planetary pattern. For every other planet, the alignment between magnetic axis and rotation axis is consistent with dynamo theory as currently understood. For Saturn, it is not. Saturn is an outlier, and outliers in science are almost always more important than the cases that fit the rule. They are the places where the rule breaks, and where the new physics hides. This is, to my mind, one of the most profound gifts that Cassini gave to planetary science. Not the confirmation of a theory, the demolition of one, the pointing of a finger at a gap in our understanding that has the width and depth of a planet. But even this mystery, compelling as it is, plays second fiddle to what Cassini found at Enceladus, because the magnetic field paradox is an intellectual challenge. What was found at Enceladus is potentially an existential one, and to understand why, we need to go back to a moment in 2005 that changed everything. In late 2004 and early 2005, Cassini performed a series of close flybys of Enceladus, a small moon of Saturn about 504 kilometers in diameter, roughly the size of the state of Arizona, or the distance from London to Edinburgh. Enceladus is primarily composed of water ice, making it one of the most reflective bodies in the solar system, brighter even than fresh Antarctic snow. It orbits Saturn at a distance of 238,020 kilometers, well inside the E-ring, the outermost and most diffuse of Saturn's major rings. On February 17, 2005, Cassini flew past Enceladus at a distance of 1,264 kilometers. The magnetometer on board recorded an unexpected distortion in Saturn's magnetic field, a bending, a deflection of the field lines around Enceladus, suggestive of interactions between the magnetic field and some kind of ionized gas or plasma near the Moon. This was already surprising. A body that small, that cold, at that distance from the Sun, was not expected to have any significant atmosphere or plasma environment. Gravity alone was far too weak to hold an atmosphere for any meaningful period of time. On March 9, 2005, Cassini flew closer, just 500 kilometers from the surface, and on July 14, 2005, it flew just 175 kilometers from the surface of Enceladus's south pole. What it found on that close south polar pass is one of the genuinely transformative discoveries in the history of planetary science. There were plumes, enormous jets of water vapor and icy particles erupting from the south polar terrain through a series of parallel fissures, immediately nicknamed the Tiger Stripes by the imaging team, each fissure roughly 130 kilometers long and 2 kilometers wide, separated by regular 35-kilometer intervals. The jets were shooting material to heights of hundreds of kilometers above the surface, far above the escape velocity of the Moon, and the material was joining the E-ring, explaining why the E-ring exists and why it is so broad and diffuse. The jets were the source of the E-ring. Enceladus was building its own ring with its own eruptions. This was already extraordinary. Active geological processes on a moon so small were not supposed to exist. The internal heat required to maintain liquid water and drive eruptions at this scale demanded an explanation, and the best one available was tidal flexing, the gravitational tug-of-war between Saturn and the nearby moon Dione, which forces Enceladus's interior to flex rhythmically, generating heat through friction. Enough heat, apparently, to maintain a liquid water reservoir somewhere beneath the ice. But the question was how deep the water was, how large the reservoir was, and what its chemistry might be. And answering those questions would take years, and dozens more flybys, and eventually a definitive gravity measurement in 2014 that demonstrated the existence of a regional subsurface ocean beneath the south polar terrain. A body of water at least 10 kilometers deep, contained under an ice shell roughly 30 to 40 kilometers thick. And then, in 2015, a global analysis of Enceladus's libration, tiny wobbles in its rotation as it orbits Saturn, that demonstrated the ocean was not regional but global, extending beneath the entire surface, ice shell floating on a planet-wide ocean. Enceladus, this tiny frozen moon smaller than the state of Arizona, has a global liquid water ocean, and it is erupting into space. But even then, even knowing about the plumes, the ocean, the tiger stripes, the discovery that closed the habitability argument, the one that genuinely changed the conversation about life in the solar system, came in 2017, and it came because Cassini flew through the plume. On October 28, 2015, Cassini made its deepest plunge yet through the Enceladus plume, passing just 49 kilometers above the south polar surface, close enough that you could fit a town between the spacecraft and the ice. At that altitude, the plume was not a distant spectacle. It was the environment. Cassini was flying through it, breathing it through its instruments, tasting the chemistry of whatever ocean lay beneath. The instruments on board Cassini that were most relevant to understanding the plume's chemistry were the Ion and Neutral Mass Spectrometer, IMS, and the Cosmic Dust Analyzer, CDA. The INMS was designed to measure the molecular masses of gases and volatile compounds in the spacecraft's immediate vicinity, essentially sniffing the local atmosphere with extraordinary precision. The CDA was designed to measure the mass, speed and charge of individual dust particles. Together, over the course of multiple plume flybys, they built up a chemical portrait of what Enceladus was releasing. The early results were already significant. Water vapour, obviously, but also carbon dioxide, molecular nitrogen, simple hydrocarbons including methane, and heavier organic compounds. The plume was not just water, it was a cocktail of organic chemistry, a molecular zoo that spoke of complex processes occurring somewhere beneath that ice shell. But the 2015 flyby was different. The closeness mattered, and the data that came back from the INMS in the weeks and months following that pass contained a signal that took the science team considerable time to properly characterise and to be confident about before publishing. It took until April 2017, the same month that Cassini's grand finale began, for the paper to appear in the journal Science. The paper reported the detection of molecular hydrogen, H2, in the Enceladus plume at a concentration of between 0.4 and 1.4% by volume. That might sound like a minor chemical footnote. It is not. It is possibly the most significant single measurement that Cassini made in its entire mission. Here is why. Molecular hydrogen, two hydrogen atoms bonded together, is not chemically stable in the presence of water and rock at moderate temperatures. It reacts. In the presence of liquid water, it reacts with dissolved carbon dioxide to produce methane and water through a process called methanation. In the presence of hot rock and water, it is produced by a process called serpentinization, in which certain iron and magnesium-bearing silicate rocks react with water to produce serpentine minerals and release hydrogen gas as a byproduct. And in the specific environment of the deep ocean floor, where seawater percolates into hot fractured rock and is superheated before being expelled back into the ocean through hydrothermal vents, hydrogen production by serpentinization is one of the primary chemical processes occurring. On Earth, hydrothermal vents at the ocean floor support entire ecosystems. Chemosynthetic bacteria use the energy released by the reaction between molecular hydrogen and dissolved carbon dioxide to build organic molecules, bypassing photosynthesis entirely, deriving their energy not from sunlight but from the chemical disequilibrium between hot hydrogen-rich vent fluids and cold carbon dioxide-rich ocean water. Above the bacteria, entire food chains build up. Worms, crabs, shrimp, fish, all sustained by the chemical energy coming up from the rock. In 1977, when the first hydrothermal vent community was discovered at the Galapagos Spreading Center, it redefined the boundaries of what biologists had considered necessary for life. Life, apparently, does not need sunlight. It needs chemistry. It needs a source of energy and a supply of the right molecules. The detection of molecular hydrogen in Enceladus's plume is, as the paper's authors noted with meticulous scientific restraint, consistent with ongoing hydrothermal activity at the floor of Enceladus's subsurface ocean. The hydrogen would be produced there, dissolve into the ocean water, and eventually reach the plume system through whatever channels connect the ocean to the surface fissures. By the time it exits through the tiger stripes, the hydrogen has not had enough time to fully react with the available carbon dioxide. The ocean is large enough, and the water is cold enough in the upper layers that the reaction kinetics are slow, so a measurable fraction exits the plume intact. What this means in the most direct terms available is this. At the bottom of Enceladus's ocean, hot water is reacting with rock. The chemistry of those reactions is indistinguishable from a measurement perspective from the chemistry occurring at hydrothermal vents on the floor of Earth's oceans. The energy source available at those vents, hydrogen reacting with carbon dioxide, is precisely the energy source that Earth's deep-sea chemosynthetic ecosystems run on. Enceladus has water, it has chemistry, it has energy, it has organic molecules. And it has been operating this way in a relatively stable state for long enough to have built a global ocean and maintained the geological activity that drives the plumes. The team working on the habitability implications was careful, as scientists are, to state explicitly that this does not mean Enceladus is inhabited. Cassini could not detect life, had no instrument capable of detecting the molecular signatures of biology at that level, but the phrase used in the discussion section of the paper, "The environment at Enceladus's seafloor may be providing conditions favourable for the emergence and persistence of life," is about as direct as a group of peer-reviewed scientists is ever going to get in saying that what they found looks like a habitable environment. I will be direct. When I read the full text of that 2017 paper, I found myself returning to a single sentence in the discussion section 3 or 4 times before I could fully absorb what it was saying. The sentence was noting that the thermodynamic calculations showed the chemical reaction between the detected hydrogen and the detected carbon dioxide. The reaction that would power chemosynthetic life was exergonic, meaning it releases energy. There is a word for a chemical environment that releases energy in a form that living systems can exploit. That word is habitable, and this is the word that best describes what Cassini found at the bottom of Enceladus's ocean. The question, the unbearable, unresolved, burning question, is what is down there, not what the chemistry is, not what the physics is. What, if anything, is living in that water, in the dark, beneath 40 kilometres of ice, in the gravitational shadow of a ringed giant 1.27 billion kilometres from the Sun? We don't know. We cannot know yet. And the reason we cannot know yet is directly connected to the decision that ended Cassini's life. There is a photograph taken on September 15, 2017, in the Mission Control Room at NASA's Jet Propulsion Laboratory in Pasadena, California. The room is full. Dozens of engineers and scientists are seated at consoles arrayed in tiered rows, each station covered with monitors displaying telemetry data, trajectory plots, signal strength readouts. At the front of the room, on the main wall display, a green spike is visible, the radio signal from Cassini arriving from Saturn with an 83-minute delay, confirming that the spacecraft is still transmitting. The room is quiet in the particular way that rooms full of people are quiet when something irreversible is about to happen. Seated near the centre of the management table is Linda Spilker. She is a planetary scientist from NASA's Jet Propulsion Laboratory, and she has spent 30 years of her life on this mission. 30 years is a number that deserves to be held for a moment before moving past it. 30 years is longer than many careers. 30 years is the span of a childhood through early adulthood. 30 years, in Spilker's case, began in 1988 when she was hired as part of the Cassini science team in the mission's earliest planning and development phase, 9 years before the spacecraft would launch. She was there for the design of the science objectives. She was there through the years of instrument construction and testing. She was there for the launch in October 1997. She was there for Saturn orbit insertion in June 2004. She became the mission's project scientist, the person responsible for the overall scientific program and for being the primary scientific liaison between the instrument teams and the mission management. And she held that role through all 13 years of orbital operations, through every close flyby of every moon, through every ring crossing, through every discovery and publication and congressional briefing. Before Cassini, Linda Spilker worked on Voyager. Her entry into space science came through the Voyager mission that visited Saturn in 1980 and 1981. providing the first close observations of the ring system. It was Voyager's hints of complexity in the rings, the thousands of ringlets and gaps, the unexpected density waves and braids, the shepherd moons, that had fired her curiosity and set the direction of her scientific life. She is, by any reasonable assessment, one of the leading experts on planetary ring systems in the world. She has published more than 130 peer-reviewed papers on subjects ranging from Saturn's ring composition to Titan's atmospheric structure to the implications of Enceladus's ocean for astrobiology. She got her first telescope at Christmas when she was in 3rd grade. She looked at stars. She has said, captivated by the question of what was out there. 60-some years later, having spent 3 decades of her professional life orbiting Saturn with the most sophisticated robotic explorer humanity had ever built, she was sitting in mission control at JPL on September 15, 2017, watching a green spike on a monitor, knowing it would disappear. Here is what is important to understand about that room on that morning, beyond the biographical facts. The people in it had not simply built a spacecraft. They had, in a very real sense, lived alongside one. Scientists and engineers had devoted their careers to Cassini, had defined their professional identities through its instruments and its discoveries. Some of them had been there for the full 20 years, from concept to conclusion. Others had joined during the mission, had done their doctoral work using Cassini data, had raised children during the years when Cassini was orbiting Saturn, had watched their parents age, and in some cases die, while Cassini continued its quiet loops around the ringed world. The spacecraft was, to the people who worked with it daily, a presence in their lives in a way that is difficult to convey to someone who has not worked on a long-duration space mission. Earl Mays, the mission's project manager, the person responsible for keeping the spacecraft operational and the mission on budget and schedule, described the team in the months before the grand finale as going through something resembling the anticipatory grief that a family feels when a loved one is terminally ill. There was work to be done, important work, the most exciting work of the mission, and they were doing it with full professional commitment. But underneath the operational routine, there was the knowledge that this was ending, that every orbit was one fewer orbit, that every flyby of Titan and Enceladus and the other moons was a last flyby. The decision to end Cassini's life in Saturn's atmosphere was not made lightly, but it was made clearly. By 2017, the spacecraft's propellant supply was nearly exhausted. Without propellant, you cannot control a spacecraft's trajectory. An uncontrolled Cassini, drifting in the Saturn system, might eventually be perturbed into a collision course with Titan or Enceladus. And if that happened, if a spacecraft containing 7 kilograms of plutonium and 22 years' worth of Earth microbiology in its component materials were to crash into either of those moons, the contamination might permanently compromise the ability of future missions to assess whether any life found in those environments was indigenous or terrestrial in origin. This is the planetary protection problem, and it is taken seriously by everyone who works in the field. The moons of Saturn that Cassini had identified as potentially habitable could not be risked. The spacecraft would be destroyed. The question was only where and how. Plunging into Saturn's atmosphere was the chosen method. The planet itself, a gas giant with no solid surface, no accessible ocean, no plausible habitat, could absorb Cassini safely. And if the spacecraft was going to be destroyed anyway, the mission team made the only decision that made scientific sense. They would use the final approach to collect data. Every instrument that could be operated was kept active. Every byte of storage and transmitter capacity was dedicated to sending home results. Cassini would work until the moment Saturn's atmosphere overwhelmed its ability to keep its antenna pointed at Earth. This is, to my mind, one of the most genuinely noble decisions in the history of scientific exploration. Not the destruction of the spacecraft, there was no choice in that, but the absolute determination that the destruction would not be wasted, that the death would be a final, generous act of measurement. Cassini was designed as a machine for understanding a planet. It would remain a machine for understanding a planet until Saturn itself dissolved it. Linda Spilker has described the morning of September 15, 2017 in several interviews, and the consistency of her account across different contexts suggests she is telling it as she genuinely experienced it. She arrived at JPL in the pre-dawn hours. She was in mission control before most of the team. She had spent the previous days reviewing the final science sequences, confirming that every instrument was configured for the entry phase, that the data rates were optimized, that the memory management was set to overwrite older data with new data so that the most recent atmospheric measurements, the deepest into Saturn's atmosphere that the instruments would ever reach, would be the last things transmitted. The grand finale passes had already been extraordinary. In the months before the final plunge, as Cassini threaded through the gap between the rings and the planet, the science returns had exceeded virtually every expectation. The gap was emptier than predicted. Not completely empty, but sparse enough that the team had quickly dropped the precautionary mode they had entered for the first dive, having braced for a sandblasting by ring particles that largely did not materialize. They named it the Big Empty. The unexpected sparseness of the gap was itself a scientific finding, suggesting that particles in the innermost ring region are being funneled out of the region by processes that were not well understood before Cassini got there. The mass spectrometer was sampling the tenuous upper atmosphere directly. The magnetometer was measuring the field from inside the ring system for the first time. The gravity measurements were building up, orbit by orbit, into the precision measurements that would constrain the ring mass, and the imaging system was sending back the closest pictures of Saturn's cloud bands ever taken. Images of individual storms and vortices in the atmosphere that would have been beyond the resolution of any Earth-based telescope, capturing detail at a scale of approximately 3 kilometers per pixel. But on September 14, 2017, Cassini made its final flyby of Titan, the last gravitational nudge that reshaped its trajectory into the terminal dive. At that point, there was no returning to a safe orbit. The spacecraft was committed to Saturn. The final orbit would take approximately 21 hours before the atmospheric entry, and during those hours Cassini continued transmitting telemetry, engineering data, the last few bits of science from instruments that were still functioning, while the team at JPL gathered. The 83-minute signal delay meant that by the time the team watching the monitors saw Cassini enter the atmosphere, Cassini had already been gone for 83 minutes. This is one of the stranger facts of deep space exploration, and I find it philosophically unsettling in a way I cannot quite resolve. When the team celebrates a success or mourns a loss, they are always celebrating or mourning something that happened nearly an hour and a half ago. The spacecraft lived and died in its own local time. The news of its death arrived as a historical record, not as a live event. At 11:55 UTC on September 15, 2017, the signal disappeared from the monitors in mission control at JPL. The green spike on the frequency plot diminished, brightened briefly, that strange, ghostly reprieve caused by the side lobe of the antenna's radio beam swinging momentarily back toward Earth as the spacecraft began to rotate, and then was gone. Silence. After 19 years, 335 days of operation, Cassini had become one with Saturn. Earl Mays, standing at the front of the room, said, "The spacecraft is gone," and then, with the particular precision of someone who had spent years managing a system with a communication delay of over an hour, "It's gone." A pause. "Thanks and farewell, Cassini." There was applause. Subdued, emotional applause, the kind that is both a celebration and a funeral simultaneously. People wept. Not many and not dramatically, but those who did were not embarrassed by it. You do not spend 30 years of your life on something and watch it end without feeling it in your chest. Linda Spilker, in interviews given afterwards, described the emotion of that morning as bittersweet, a word she has returned to repeatedly, suggesting it is the most honest and precise description she has found. There was sorrow, genuine sorrow, at the ending of something she had dedicated so much of her life to, And there was the parallel knowledge, the professional understanding that the data Cassini had sent home over those final months and years would sustain research programs for decades. The spacecraft was gone, but the discoveries were not. The discoveries were in the data, archived at JPL and at institutions around the world, being analysed, cross-referenced, disputed, refined, extended, and published in the scientific literature at a rate that has continued undiminished for years after Cassini's destruction. As of the preparation of this script, the Cassini mission has produced more than 948 peer-reviewed scientific papers. That number was at roughly 3,000 at the time of the spacecraft's destruction in 2017. In the years since, the data, the raw numbers sent home over 9 billion kilometers of radio signal, have continued to yield new findings. A paper published in the journal Nature in 2019 used grand finale gravity data to constrain models of Saturn's interior structure in ways that were not possible before. A 2021 paper used Cassini ring imaging to track the evolution of a propeller-shaped structure in the A ring, a local disturbance caused by the embedded moonlet Blériot, and from its trajectory changes infer something about the density and viscosity of the ring material around it. A 2022 paper revisited the IMS atmospheric composition data from the final plunge and found additional chemical signatures, silicone-based compounds, further confirmation of ongoing geological activity that had been initially masked by calibration challenges. Cassini is still doing science. It is just doing it from the archives rather than from orbit. Linda Spilker's life after Cassini continued at JPL. She was appointed Chief Scientist of JPL in 2018, a role that recognises both her scientific stature and her broader institutional leadership. She remains actively involved in planetary ring science, in the planning for future missions to the outer solar system, and in the advocacy for a mission to Enceladus that she and her colleagues have worked toward since well before Cassini's end. She is, by her own account, still thinking about the data, still pulling threads, still finding things in the numbers that Cassini sent home that prompt new questions. That is the nature of the data Cassini collected. It is not finished speaking, but the question that its final months raised most loudly, the question about the gap, about the magnetic field, about the rings, about Enceladus, is not a question that can be answered from the archive alone. At some point, humanity will have to go back, and what we send next will be shaped fundamentally by what Cassini found. What, though, were the precise physical details of those last 91 seconds? What was the spacecraft's body doing? What were its instruments recording? And what does the engineering reconstruction of those final moments tell us that the data alone cannot? Cassini was not built to fly into a planetary atmosphere. This point cannot be overstated. The spacecraft was designed to orbit in the near vacuum of interplanetary space, where the external forces acting on it are gravitational, predictable, calculable, manageable with small thruster corrections every few days. The structure of Cassini was not aerodynamically optimized. There was no heat shield, no ablative coating, no reinforced leading edge. The 11-meter magnetometer boom protruding from the spacecraft's side was not a feature engineered for atmospheric entry. It was a sensor arm designed for measurements in free space, and its presence in an atmosphere would make the spacecraft behave like a weather vane in a hurricane. At approximately 900 kilometers above Saturn's cloud tops, roughly the altitude where the density of Saturn's outermost atmospheric layers transitions from being cosmetically negligible to being physically meaningful, Cassini began its final engagement with Saturn. The time was approximately 0444 Unidicity on September 15, 2017. Coincidentally, almost exactly 20 years after launch, the spacecraft was travelling at approximately 123,000 kilometers per hour relative to Saturn. At that speed, even the thinnest wisps of hydrogen and helium that constitute the upper atmosphere exerted measurable dynamic pressure against the spacecraft's surfaces. The magnetometer boom felt it first. 12 meters long, extending from the spacecraft's body, exposed to the incoming atmospheric flow at a substantial angle, It functioned exactly as a lever. The tenuous gas pressed against its length, generating a torque that began to rotate the spacecraft, slowly at first, then with increasing authority, in the direction that would swing the high-gain antenna away from Earth. Cassini's attitude control system responded immediately, as it was designed to do. The spacecraft used a bang-bang control approach. The spacecraft was given a permitted rotation range of just 2 milliradians, or 0.1 degrees, and whenever its actual orientation reached the edge of that range, a thruster fired to push it back toward the centre. Each attitude control thruster could produce approximately half a newton of force, the weight equivalent of a tennis ball resting on Earth's surface. 8 of these small thrusters were the last line of defence between Cassini's transmitting antenna and silence. At first, the thrusters fired every few minutes, brief pulses to nudge the spacecraft back into alignment. As Cassini descended and the atmospheric density increased, the corrections became more frequent and longer. The forces acting against the spacecraft's structural protrusions, the boom, the antenna dish itself, the instrument platforms extending from the body, grew stronger with each passing second. For 91 seconds, the battle went Cassini's way. During those 91 seconds, the spacecraft was live-streaming data from 8 science instruments simultaneously. The ion and neutral mass spectrometer was measuring the molecular composition of the atmosphere being encountered. Direct, in situ sampling of Saturn's uppermost atmospheric layers, something that had never been done before. The magnetometer was recording the magnetic field from the deepest point it had ever reached. The plasma spectrometers and energetic particle detectors were measuring the charged particle environment. The radio and plasma wave science instrument was listening to the electromagnetic environment, and the engineering telemetry, the thruster firing records, the attitude control data, the power consumption measurements, was itself a scientific record of atmospheric density and dynamics. During those 91 seconds, the mass spectrometer sniffed hydrogen, helium, water, methane, ammonia, carbon monoxide, nitrogen, and carbon dioxide, more complex than the models had predicted, with organic compounds present at levels suggesting a rain of ring material into the atmosphere that was actively altering its chemistry. The atmosphere was not pristine gas. It was contaminated, in the most scientifically productive sense, by the very rings that surrounded it. During those 91 seconds, the magnetic field measurements tightened the constraint on the tilt to below 0.0095 degrees. The final, most precise measurement that would go into Doherty's science paper the following year. And during those 91 seconds, the thrusters went from gentle corrective pulsing to a sustained, maximum capacity firing that used every newton of force they were capable of generating. In the last 20 seconds before signal loss, the thrusters were running at 100% of their design capacity. Cassini was not going quietly. It was fighting with every millinewton available to it to keep that antenna pointed at Earth for one more second of data. Julie Webster, Cassini's spacecraft operations chief, has described the feeling of watching the telemetry reconstruction afterward as profoundly moving. The data showed that the spacecraft never gave up its orientation voluntarily. It fought the atmosphere until the physics of the situation were simply beyond its ability to overcome. In the final 8 seconds, the antenna began to slip. Slowly, irrevocably, the boom winning its battle against the thrusters as Saturn's atmosphere thickened around the spacecraft. The antenna rotated away from Earth. The beam narrowed, the signal weakened, showed that ghostly brief strengthening as the side lobe swept across Earth's direction, and then ceased. At the altitude and velocity Cassini was travelling, atmospheric heating would have been building rapidly in those final seconds. Aerodynamic heating scales with the square of velocity, and at 123,000 kilometers per hour, the thermal input was enormous. Without a heat shield, Cassini's components would have been reaching their design temperature limits within seconds of the antenna going silent. The gold-foil thermal blankets would have stripped away. The instrument housings, the electronics boards, the structural members. All of it was being converted into heat and plasma, Cassini's physical substance merging into Saturn's atmosphere at the molecular level. Within minutes of signal loss, Cassini effectively ceased to exist as a discrete object. Its atoms, titanium, aluminium, copper, platinum, plutonium, scattered into Saturn's upper atmosphere, diffusing into the currents of a planet that weighs 683 times 10^² fish kilograms. The spacecraft's contribution to Saturn's mass was negligible to the point of immeasurability, but its contribution to Saturn's scientific record was, by any reasonable measure, permanent. What is worth dwelling on here is a structural paradox that I find haunting whenever I think about those final moments. The atmosphere that was tearing Cassini apart was also the atmosphere that Cassini was measuring. The very process of destruction was the measurement. The thicker the atmosphere became, the harder the battle, and the harder the battle, the more the engineering data told the team about the atmospheric density profile. Cassini's death was also Cassini's final experiment. It could not have designed a more complete scientific exit, and what the data from those last 91 seconds confirmed, together with the data from the preceding 22 grand finale orbits, is that Saturn's atmosphere is not a simple layered gas envelope. It is in active chemical communication with the ring system above it. The rings are not separate. They are connected electrically, gravitationally, chemically to the atmosphere below. Material from the rings rains continuously into Saturn at a rate of between 4,845 zeros and kilograms per second, depending on the region and the measurement methodology. That range includes the ring rain driven by magnetic forces and the equatorial infalling of electrically neutral particles dragged in by Saturn's upper atmospheric winds. Two separate mechanisms, operating simultaneously, both moving ring material into the planet at a rate that could drain the entire ring system in somewhere between 100 and 300 million years. This is one of the more quietly alarming numbers in the entire Cassini dataset. It was already known before the grand finale that ring material was falling into Saturn. Voyager had seen the dark bands in the stratosphere that Jack Connolly identified as ring rain signatures in 1986. Earth-based observations had confirmed it, but the rate at which Cassini measured it from inside the gap was at the high end of previous estimates. Saturn's rings are not stable. They are actively draining. They formed perhaps 100 million years ago. They are currently eroding at a rate that is measurable on geological timescales, and they will be gone in somewhere between 100 and 300 million years from now. What created them 100 million years ago? Something gravitationally disrupted, probably a moon or a number of moons whose orbital paths were perturbed until they crossed the Roche limit. The distance from Saturn, inside which tidal forces are stronger than the structural strength of a solid body, causing it to be torn apart rather than remaining whole. The debris spread into a disk. The disk settled into the spectacular, thin, bright structure we see today, and it is currently, slowly, inexorably falling home. This is the second great escalation of the Cassini story. We are not looking at a permanent feature of the solar system. We are looking at a temporary one, caught in its relative prime, its architecture already compromised by the same physics that created it. Saturn's rings are, in the grand timescale of solar system history, a brief apparition, a cosmic firework display that started when dinosaurs were walking the Earth, and will be finished long before any evolution on this planet produces a creature capable of looking up and grieving their absence. There is a specific sadness in that image that I did not expect to feel when I first began researching this video. The rings of Saturn, which have been the most recognizable feature of the solar system for every human being who has ever lived, for every astronomer, every child who ever looked through a telescope, every science fiction writer who ever set a story in the outer solar system, those rings are a temporary gift. We, specifically, are the civilization fortunate enough to exist during the small window when they are fully formed and maximally brilliant. Future civilizations, if they exist, will see a progressively less ornamented Saturn, the rings thinning and dimming as the material continues to fall. until one day, perhaps 200 million years from now, perhaps 300 million, they simply aren't there anymore. That realization, more than any single technical discovery, is what I keep returning to when I think about what Cassini found. Not just the science of it, the meaning of it, the temporal contingency of beauty. We should be careful here, because the history of planetary science is absolutely littered with premature certainties that later required substantial revision. Every major discovery in the Cassini dataset carries with it a set of caveats, ongoing debates, and alternative interpretations that the simplified version of the story tends to smooth over. And if we are going to take the science seriously, which we should, because the science is more exciting than any simplification of it, we need to sit with the complications, start with the rings. The conclusion that Saturn's rings are between 10 and 100 million years old, derived from the grand finale gravity measurements, combined with contamination modelling, is not universally accepted in its strongest form. The mass measurement itself, approximately 15 Mimas masses for the main ring system, is now one of the most precisely determined facts about the ring system, and there is no serious dispute about the number. The dispute is about what you conclude from it. The contamination model that converts ring mass and brightness into an age estimate depends on assumptions about the flux of dark material, the rate at which interplanetary dust and micrometeorites are hitting the rings and darkening them. This flux has been measured by multiple instruments and estimated by multiple methods, but the uncertainty in it is not negligible. If the dust flux in Saturn's neighbourhood is at the lower end of current estimates, then the rings could be somewhat older than 100 million years. Some analyses suggest an upper bound of 400 million years is defensible. Others, using independent methods, including measurements of the abundance of nanometer-scale silicate grains embedded in ring material, point toward the younger end, potentially as little as 40 to 50 million years. What nobody now credibly argues is that the rings are 4.5 billion years old. That hypothesis is dead. The old hypothesis was that Saturn formed with its rings, and the rings have been there ever since, gradually evolving but fundamentally primordial. Cassini killed that hypothesis with the precision of a correctly aimed measurement. What remains is a narrower range of young ages, with the precise figure somewhere between tens and a few hundreds of millions of years, depending on the assumptions you make about the dust flux and the degree to which the B ring, the most massive, most opaque, most complicated ring, has been absorbing and sequestering incoming dark material in ways that might have slowed its apparent darkening. This is not a trivial distinction. The difference between 50 million years and 400 million years, in terms of what event created the rings, is potentially the difference between a disrupted small moon in the relatively recent geological history of the solar system and a disrupted body from a more dynamically active period in the middle history of Saturn's moon system. The event that created the rings, whatever cosmic catastrophe produced 160 kilometers worth of nearly pure water ice distributed in a disk, is not the same event in both cases. One leading hypothesis, developed by Matija Chuk of the SETI Institute and colleagues, connects the youth of the rings to a broader remodelling of Saturn's moon system that may have occurred around the same time, roughly 100 million years ago. The hypothesis involves a dynamical instability in the orbits of Saturn's inner moons, potentially triggered by a resonance crossing as the moons slowly migrated outward under the influence of Saturn's tides. In this scenario, some of the inner moons at the time collided or were tidally disrupted, providing the material for both the current ring system and potentially reshaping the orbital configuration of the surviving inner moons. It is a hypothesis that connects the rings, the moons, the tidal interactions, and the ring mass into a single coherent narrative. But it is a hypothesis. It is not yet confirmed. The data from the grand finale constrains it strongly in some respects, and leaves it underspecified in others. The precise origin of the ring material, which body or bodies were disrupted, where they were when they were disrupted, What their composition was that produced such pure water ice remains an open question that no current or planned mission is specifically designed to answer. Now turn to the magnetic field problem, which is, if anything, even more bristling with unresolved complications. The measurement that the magnetic tilt is less than 0.0095 degrees is solid. The Doherty Group's 2018 science paper is methodologically careful, with extensive error analysis and multiple cross-checks between different measurement methodologies. The residual tilt could be zero, or it could be some small but non-zero value below the measurement threshold. Either way, it is dramatically smaller than any other measured planetary magnetic field. The question is what to do with that fact. The stratified filtering layer hypothesis, the idea that helium demixing creates a stably stratified zone above the dynamo that selectively removes the asymmetric component of the field, is the most developed theoretical response, and it has been elaborated in considerable detail by Sabine Stanley at Johns Hopkins University and others. The core of the argument is that a stably stratified, slowly rotating shell of fluid around the dynamo region would preferentially damp magnetic field variations on timescales comparable to the ohmic decay time of the fluid, which for the relevant materials and temperatures is of order tens of thousands of years, while preserving the axisymmetric component. This is physically reasonable. It is not absurd, but it requires that the filtering be essentially perfect, that whatever residual tilt emerges from the stratified layer be reduced to below 0.0095 degrees, and the tuning that would be required to achieve this level of alignment consistently is itself something that needs to be explained. Why is Saturn's interior arranged in such a way as to produce such precise filtering? One answer is, it isn't tuned precisely, and we are looking at the current state of a dynamically evolving system that happens to be passing through a moment of near alignment. Saturn's dynamo may oscillate, with the filtered tilt varying over geological timescales, and we happen to be observing it near a minimum. This is possible, but it requires the oscillation timescale to be long relative to the age of the present measurement campaign, which is hard to test without a very long baseline of measurements. Another answer is genuinely radical. Saturn's dynamo is somehow fundamentally different from every other planetary dynamo we know about. Perhaps the interior structure, the distribution of metallic hydrogen, the depth and configuration of the helium demixing layer, the rotation profile with depth, conspires to produce a different regime of magnetohydrodynamic dynamics than anything we have modelled, one in which near-perfect alignment is a natural attractor rather than an impossibly coincidental state. This is the frontier of a discipline called planetary magnetohydrodynamics, and it is frontier in the literal sense. We do not have definitive answers. We have models, some more constrained by data than others, and we have the measurement itself, sitting there at less than 0.0095 degrees, refusing to give up its secret. Since Cassini's end, additional analysis of the grand finale magnetic data has attempted to extract higher-order components of the field, the quadrupole and octupole terms, that might reveal something about the dynamo structure even if the dipole is nearly perfectly aligned. Some of this work suggests that the higher-order terms do carry information about the interior structure, and that their patterns are consistent with a deep-seated dynamo confined to a region closer to Saturn's core than Jupiter's dynamo, perhaps reflecting the different composition and pressure profiles of the two gas giants. But the constraints from these higher-order measurements are still relatively loose, and definitive conclusions await both more sophisticated modelling and, ultimately, more precise measurements than any current or funded mission can provide. Then there is Enceladus. The habitability implications, rich as they are, come with their own set of complications. The hydrogen measurement, the detection of molecular H2 in the plume at concentrations consistent with ongoing hydrothermal activity, was published in 2017 and has been widely accepted in the community. But the inference from hydrothermal activity to conditions favourable for life is a significant step. and it rests on an analogy between Enceladus's ocean and Earth's deep-sea hydrothermal environments that has limits. On Earth, chemosynthetic ecosystems at hydrothermal vents are embedded in a biosphere that has been evolving for at least 3.5 billion years. The bacteria that colonize vent environments are not the product of a spontaneous chemical genesis happening in real time. They are the product of a long evolutionary history derived from ancestors that developed the necessary enzymatic machinery over billions of years of prior biological evolution. The question of whether life could independently emerge at Enceladus's vents, as opposed to simply persist there if it were somehow seeded, is a genuinely different question, and one that the chemistry alone cannot answer. The ingredients are present, the energy is present, the liquid water is present, the organic chemistry is present, but the presence of the ingredients for life does not guarantee the emergence of life. We have exactly one data point for abiogenesis, one case we know of in which life emerged from chemistry, and that is Earth. We do not know how probable abiogenesis is, how much time it requires, what specific conditions favour it, or whether the conditions at Enceladus are in the right range. What Cassini did was demonstrate that Enceladus satisfies every constraint we currently know how to check. It meets the known requirements. Whether it also meets some requirements we don't know about yet, we cannot say. This is not a failing of the data. It is a limitation of the question. The question of whether life exists at Enceladus can only be answered by going to Enceladus and looking for it directly. And the detection method for life in a subsurface ocean, accessible only through its plume eruptions, is itself a formidable technical challenge. What molecular signatures would unambiguously indicate biology? Complex amino acids? Chirality, the preferential handedness of organic molecules that on Earth reflects the asymmetric chemistry of living cells. Isotopic fractionation patterns consistent with metabolic processing of carbon. All of these signatures have been proposed, and all are theoretically detectable by mass spectrometers of sufficient capability. But none have yet been measured at Enceladus, because the instrument that flew through the plume, Cassini's INMs, was not designed with these specific biosignatures in mind. The INMs was an extraordinary instrument built in the 1990s for a general survey of molecular masses and abundances. It was not an astrobiology instrument. The next mission to Enceladus, if one is sent, will be. There is also the question of the organic chemistry in the plume that is more complex than the initial reports suggested. Papers published between 2018 and 2022 using more sophisticated analysis of the Cassini CDA and INMS data have identified aromatic and aliphatic hydrocarbons in the plume material, complex organic molecules with masses above 100 atomic mass units well into the range of biological molecules. These were detected in both the gas phase and in the nanograin particles of the plume. Their presence does not indicate biology. Complex organics can be synthesized abiotically by a variety of chemical pathways, but their complexity and diversity is consistent with active, sustained organic chemistry in a liquid water environment over a substantial period of time. Some of the most intriguing recent reanalysis of the Cassini data has focused on identifying which specific classes of organic molecules are present. The presence of oxygen-bearing organic compounds, aldehydes, ketones, or compounds with nitrogen-bearing groups would be particularly diagnostic, as these classes are more energetically demanding to synthesize abiotically and are more central to the chemistry of life as we know it. Early reanalysis suggests these classes may be present in the data, but the mass resolution of the INMs makes definitive molecular identification challenging at the higher mass ranges where these compounds appear. What the complications collectively underscore is that Cassini's data is not a finished document. It is a starting point. The mission closed one chapter of Saturn science, the era of orbital reconnaissance from outside the ring system, and opened another that cannot be completed without new missions. The ring's age is now constrained, but not definitively determined. The magnetic field anomaly is measured with extraordinary precision, but not explained. The the habitability of Enceladus is demonstrated in terms of necessary conditions, but not sufficient ones. The organic chemistry of the plume is characterized at a general level, but not resolved at the molecular level. And then there is Titan. Titan, Saturn's largest moon, with its thick nitrogen atmosphere, its methane weather cycle, methane rain, methane rivers, methane lakes and seas, and its complex organic photochemistry that produces a global haze of tholins that colour the moon a deep, burnt orange. Cassini observed Titan in more than 100 targeted flybys over 13 years, mapping its surface through the haze using radar, infrared imaging, and near-infrared spectroscopy. The Huygens probe, delivered by Cassini and descended through Titan's atmosphere in January 2005, provided 72 minutes of surface-level data, the most distant in-situ measurement ever taken from a planetary surface before its batteries were exhausted. What Cassini's 13 years of Titan observation revealed is a world of staggering complexity. The methane cycle on Titan is, in structural terms, almost perfectly analogous to the water cycle on Earth. Evaporation from the surface, atmospheric transport, cloud formation, precipitation, runoff through river channels, collection in lakes and seas. The largest of the methane seas, Kraken Ma, in the northern hemisphere, has a surface area of approximately 400,000 square kilometres, comparable to the Caspian Sea. The rivers feeding it, channels etched into water ice bedrock by millennia of methane flow, are clearly visible in the Cassini radar data, sinuous and dendritic, their patterns unmistakably the signatures of liquid erosion. Titan is cold, very cold. Its surface temperature is approximately 179 degrees Celsius, cold enough to liquefy methane but far too cold for liquid water on the surface. The lakes and seas are methane and ethane, not water. Any chemistry occurring in them is happening in a solvent that is radically different from water, at temperatures that are too low for conventional biochemistry. Whether any form of life could exploit this environment, using acetylene as a metabolic energy source, perhaps, or operating with a cell membrane chemistry based on nitrogen compounds rather than phospholipids, is an open and actively investigated question. Theoretical biologists have speculated about it, producing chemistry models that are internally consistent but entirely conjectural in the absence of data. The search for life at Titan, if it occurs, will be a search for life that is fundamentally unlike any life we know. And here is where the implications of Cassini's discoveries both at Titan and Enceladus collide with each other in a way that has profound consequences for our understanding of where life might exist in the universe. Before Cassini, the conventional view was that life required liquid water, and liquid water required proximity to a star, the habitable zone, defined by orbital distance, the Goldilocks region where temperatures allow water to exist as a liquid. Enceladus violates this model entirely. Enceladus has liquid water not because of its proximity to the Sun, but because of the tidal heating generated by its orbital relationship with Saturn and Dione. It is habitable in the relevant sense because of gravitational energy rather than solar energy. This has enormous implications for the frequency of potentially habitable environments in the galaxy. If life can be sustained by tidal heating rather than stellar radiation, then the habitable zone ceases to be a narrow orbital band around a star and becomes instead a characteristic of moon systems around any sufficiently large planet. Every gas giant, every ice giant, in every stellar system potentially hosts moons in the Enceladus situation. Europa at Jupiter, possibly Ganymede, potentially moons of ice giants in other star systems. The habitable volume of the galaxy, under this revised understanding, is orders of magnitude larger than the stellar habitable zone model predicts, and that, if it holds, is a revision that rewrites the probability calculations for the occurrence of life throughout the cosmos. This is not Cassini's conclusion alone. The possibility of subsurface oceans powered by tidal heating had been proposed for Europa before Cassini arrived at Saturn. But Cassini's work at Enceladus converted the possibility into a concrete example, provided the chemical data that placed Enceladus solidly in the habitable category, and gave the concept of tidal habitability a specific, measured, analysable anchor in the real solar system rather than a theoretical abstraction. That is what missions do that theories cannot. They provide the specific case, the number you can measure, the plume you can fly through. The standard narrative of space exploration treats each mission as a self-contained chapter. A spacecraft is built, launched, arrives at its target, collects data, and the chapter ends when the mission ends. The Cassini story does not fit this narrative, and it is worth being explicit about why. Cassini did not end science at Saturn, it reorganized it. The discoveries made in its final months, the ring age, the magnetic field anomaly, the habitability evidence at Enceladus, the complexity of Titan's organic chemistry, constitute not a completed picture but a revised set of priorities. They tell us, with considerable precision, what questions most urgently require answers, and what kind of missions would be required to answer them. The most pressing of these is Enceladus. Among planetary scientists who work on astrobiology and solar system exploration, the case for an Enceladus life detection mission has become, since the 2017 Plume hydrogen paper, one of the most compelling arguments in planetary science. The reasoning is straightforward. Enceladus is erupting its interior into space. A spacecraft flying through that plume does not need to land on the moon, drill through its ice shell, or deploy a submarine into its ocean. It just needs to fly through the plume with instruments capable of detecting the molecular signatures of biology at the level of concentration present in the erupted material. The moon is doing the hard work of sample return itself. What is needed is an instrument package significantly more capable than Cassini's INMs, capable of resolving organic molecules at high masses, of detecting chirality or isotopic fractionation, of distinguishing biological from abiotic organic chemistry with sufficient confidence to make a definitive claim. Such instruments exist in prototype form on Earth. The challenge is miniaturizing and hardening them for a deep space mission environment. Several concepts for an Enceladus life detection mission have been proposed and studied. The Enceladus Life Finder, or ELF, was a concept studied by a team that included Linda Spilker, targeting a series of close plume flybys with a next-generation mass spectrometer capable of the required biosignature detection. The Enceladus Orbelander, proposed to NASA's Planetary Decadal Survey published in 2022, was a more ambitious concept combining an orbiter that would make multiple plume flybys with a lander that would ultimately descend to the surface and directly sample the fresh plume material that continuously coats the South Polar terrain. The 2022 Decadal Survey, the 10-yearly prioritization exercise in which the planetary science community collectively decides which missions deserve the highest priority for funding and development, ranked an Uranus orbiter and probe as its top large mission priority for the next decade. But the Enceladus Orbelander was highlighted as a high-priority mission for the following decade, and it was included among the major recommended missions. The word following decade means the 2030s. It means that if the mission receives the funding and programmatic support required to proceed, development might begin in the mid to late 2020s, with a launch in the 2030s and arrival at Enceladus in the 2040s. We are, in other words, talking about an answer to the question of whether Enceladus is inhabited that is at minimum 15 to 20 years away, and more realistically 25 to 30 years away. Science moves at the pace of orbital mechanics and government budget cycles. There is no shortcut. In the meantime, the next Saturn system mission is likely to be focused on Titan rather than Enceladus. NASA's Dragonfly mission, a rotorcraft lander, a nuclear-powered helicopter the size of a car, is currently scheduled for launch in July 2028 and arrival at Titan in 2034. Dragonfly will fly to dozens of different surface locations on Titan, covering hundreds of kilometers over the course of its primary mission, sampling the organic chemistry of Titan's surface at multiple geological contexts. Dune fields of organic sand grains, impact craters where the surface ice has been melted and re-solidified, exposing briefly a liquid water environment, and eventually the Selk impact crater, Their models suggest water and ammonia were liquid for thousands of years following the impact, potentially allowing complex organic synthesis. Dragonfly cannot search for life by the standard definition. It is too cold at Titan's surface for conventional biochemistry. What it is searching for are the organic precursors to life, the molecules that, given the right conditions, could constitute the building blocks of a biochemistry. And, in the context of impact craters, it is searching for evidence of what happens when those precursors are briefly exposed to liquid water. If the organic molecules in Titan's environment are, as some researchers hypothesize, complex enough to produce self-organizing chemical structures in the presence of water, then the crater floors of Titan may be some of the most productive prebiotic chemical laboratories in the solar system. Brief windows into chemistry that on Earth was followed by the emergence of life, but on Titan lacks both the sustained liquid water and the warmth to take the next step. Dragonfly is a direct child of Cassini. Its science objectives were shaped by 13 years of Cassini observation of Titan's surface composition, atmospheric chemistry, and river and lake systems. Its landing site selection relied on Cassini's radar maps of the surface, which remain the highest resolution maps of Titan's surface available to mission planners. Its understanding of the thermal and electrical environment it will encounter was informed by Cassini's measurements of Titan's ionosphere and atmospheric electricity. Without Cassini, Dragonfly could not have been designed with the precision that mission planners currently believe makes it viable. The parent mission enabled the child mission in the most literal and complete sense. For the magnetic field problem, the nearest horizon is somewhat more distant. The instruments required to further constrain Saturn's interior dynamo structure would ideally be carried on a new orbiter that could operate close to Saturn, as close as the grand finale orbits, or closer, for an extended period, building up a higher precision dataset of the higher order magnetic field terms that contain information about the dynamo's spatial structure. This is technically feasible, but requires a mission with a sustained proximity orbit above Saturn, which was only possible for Cassini because the grand finale was the mission's final phase and the spacecraft could be expended. A new mission that sought to replicate the grand finale orbits for science purposes would need to plan for it from the outset, with the attendant planetary protection considerations and mission design constraints. Proposals for Saturn probes that would descend into the atmosphere, similar in concept to the Galileo probe that entered Jupiter's atmosphere in 1995, have been studied as candidates for providing direct interior composition measurements that would help constrain dynamo models. The depth distribution of helium relative to hydrogen, in particular, is a critical parameter for the stratified filtering layer hypothesis. If helium is indeed demixing and raining into the planet's deeper layers, the composition profile above the dynamo layer should reflect this, with a helium-depleted upper layer and a helium-enriched deep layer. A probe that descended deep enough to pressures of roughly 10 to 100 atmospheres, far deeper than Cassini's atmospheric measurements during the grand finale, could in principle measure this directly. No such probe is currently funded or in development. It is on the wish list, the scientific community's long-horizon set of aspirations, but it has not yet been converted into a mission concept with a budget line and a launch date. What this means practically is that Saturn's magnetic field will remain anomalous and unexplained for at minimum another decade, and probably 2 or 3. The ring age question, meanwhile, will be advanced by the James Webb Space Telescope's observations of Saturn, which have already produced new data on the ring composition and the subtle colour variations across the ring system that reflect contamination history. Webb cannot measure the ring mass that required the proximity of the grand finale gravity measurements, but it can add to the understanding of the contamination chemistry, which feeds the age modelling. The telescope has already produced the sharpest mid-infrared images of Saturn ever taken from Earth's vicinity, revealing features in the ring structure that were not previously resolved and the analysis of these data is ongoing. Beyond the specifically Saturn-focused questions, there is the broader implication of Cassini's habitability findings for the design of future deep space missions. The concept of the ocean worlds, bodies in the outer solar system harbouring subsurface liquid water, maintained by tidal heating, has been dramatically validated and extended by Cassini's work at Enceladus, building on the earlier evidence for Europa's ocean at Jupiter. The realization that these worlds are not exotic exceptions, but potentially a common category of solar system body, has reshaped the priorities of the planetary science community. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in April 2023 and will arrive at the Jupiter system in July 2031, conducting flybys of Europa, Ganymede, and Callisto before entering orbit around Ganymede. Its primary science objectives include characterizing the potential habitability of the Jovian ocean worlds. NASA's Europa Clipper, launched in October 2024, will arrive at Jupiter in April 2030 and conduct 49 close flybys of Europa, with an instrument suite that directly inherits design lessons from the Cassini experience, including mass spectrometers optimized for detecting organic molecules and biosignatures in Europa's plume material, if Europa does indeed have active plumes, the evidence for which is currently suggestive but not definitive, unlike Enceladus's plumes, which are unambiguous. The methodological template that Cassini established, fly through the plume, sample the material, constrain the chemistry, publish the habitability assessment, is now the standard approach for assessing ocean world habitability. Cassini invented this approach by necessity, not by design. The Enceladus plumes were not expected before Cassini arrived, and the science of plume sampling was improvised in real time as the discovery unfolded. The fact that this improvisation produced one of the most significant habitability assessments ever made from a spacecraft is testament both to the quality of Cassini's instruments and to the intellectual agility of its science team. We are, in 2026, living in a period where the question, "Is there life in the solar system beyond Earth?" has gone from being a speculative hypothesis to being a specific, targeted, addressable scientific investigation. Cassini did not answer the question, but it located it with much greater precision than anyone had managed before, and it produced the evidence that made the question worth the billions of dollars and decades of work that a mission to Enceladus will require. That is not a minor contribution to human knowledge. It is, in the strict sense of the word, a civilizational one. The question of what Cassini found in its final seconds is, at the surface level, a question about atmospheric chemistry and thruster firings and magnetic field measurements. But at its deepest level, it is a question about what kind of universe we live in, whether it is a universe that created life once, in one location, as a vanishingly improbable accident that will not be repeated elsewhere, or whether it is a universe that creates life wherever the conditions are met, including in the dark oceans beneath the ice of a small, erupting moon 1.27 billion kilometers from the Sun. Cassini's final seconds did not answer that question. Nothing we currently possess can. But those final seconds, and the months of extraordinary science that preceded them, performed the essential scientific act of transforming a philosophical speculation into a set of testable hypotheses about a specific place with specific measurements that either confirm or refute them. Science at its best is not the accumulation of certainties. It is the progressive, systematic replacement of vague unknowns with precise ones. Cassini replaced vague guesses about Saturn's rings with a precise age range. It replaced theoretical speculation about subsurface oceans with measured chemical evidence of a habitable environment. It replaced a theoretical anomaly about Saturn's magnetic field with a measured anomaly accurate to 3 significant figures. It replaced Saturn is the planet with the rings with Saturn is a planet whose rings we almost certainly witnessed at the peak of their temporary existence, formed by a geological event that occurred while the dinosaurs were still diversifying. None of these are complete answers. All of them are better questions, and every better question is a step toward whatever comes next. It takes light 83 minutes to travel from Saturn to Earth. This means that when the team in mission control saw Cassini's signal disappear on the morning of September 15th, 2017, they were witnessing an event that had already been over for an hour and 23 minutes. Cassini had already burned. Its atoms had already dispersed into Saturn's hydrogen clouds. The spacecraft that had launched in 1997, that had swung around Venus twice, and Earth once, and Jupiter once, that had fired its engine for 96 minutes to break into Saturn orbit, that had delivered the Huygens probe to Titan's surface, that had discovered the plumes of Enceladus and the molecular hydrogen that spoke of hydrothermal vents and possible life. All of that was already gone, had been gone since before most of the team at JPL finished their morning coffee. They were watching history. They did not know it yet because physics would not let them. There is something in that delay that mirrors the whole enterprise of science. We are always looking at light that left its source some time ago. The universe we observe is always the universe as it was, never as it is. Every star we see is a historical record. Every galaxy is a fossil of a moment long past. We navigate the present by reading the past, and we extrapolate from what we can measure to what we believe must be true. The 83-minute delay between Cassini's death and its news arriving at Earth is, in miniature, the condition in which all of science operates. What makes science different from other ways of dealing with this fundamental uncertainty is not that it eliminates the delay. It doesn't. It is that it quantifies it, accounts for it, incorporates it into the measurement. It knows when the light left. It knows how far it travelled. It can back-calculate what the source must have looked like when the light left, and correct for the journey. Science does not pretend that the gap between observation and reality does not exist. It works with the gap. It treats the gap as information Cassini's data, all 635 gigabytes of it, sent home over 13 years, including those last 91 seconds of atmospheric entry, will continue to be analysed for decades. Researchers who are currently in secondary school will write their doctoral dissertations on aspects of the Cassini dataset that have not yet been fully interrogated. The question of Saturn's magnetic tilt will be worked on by scientists who are currently learning calculus. The question of whether Enceladus's hydrothermal vents are inhabited will be answered, or not answered, by a mission that has not yet been approved or funded or designed, operated by people who have not yet chosen their careers. We are, on the timeline of this discovery, very early. What feels like an ending, September 15th, 2017, the signal disappearing, the green spike flattening on the monitor in JPL mission control, is not an ending at all. It is the point at which the baton was passed. Cassini did what it was built to do. It went somewhere, it looked carefully, it told us what was there. The telling is over. The understanding is just beginning. Linda Spilker, asked in the years since the mission's end what she thinks about when she looks at Saturn through a telescope, said something that has stayed with me since I read it. She said that she no longer sees Saturn the way she saw it before the mission. Before Cassini, Saturn was a beautiful, mysterious object, the ringed world, the jewel of the solar system. After Cassini, she sees it as a system, a dynamic, interconnected, chemically active complex of bodies in constant conversation with each other. She sees the rings not as a static feature, but as a temporary ornament falling home. She sees the tidal forces that heat Enceladus. She sees the methane rains of Titan. She sees the magnetic field threading through all of it, anomalously aligned, inexplicably persistent. When she looks at Saturn now, she says, "It is like looking at a photograph of a friend. You see not just the face, but everything you know about the person behind it." That is what Cassini gave us. Not just data, not just the numbers, though the numbers are extraordinary and precise and the basis of everything that follows. It gave us intimacy with a planet. It gave us the right to say that we know Saturn. Not completely, not definitively, not without mysteries that will take generations to resolve, but as a physical reality rather than a distant point of light. There is, somewhere in the outer solar system right now, an ocean that no sunlight has ever touched. It is kept liquid not by any star, but by the rhythmic tidal squeezing of a planet that weighs 568 quintillion kilograms. On the floor of that ocean, hot water is reacting with fractured rock, releasing hydrogen, producing the chemical disequilibrium that powers the deepest ecosystems on Earth. Whether anything alive swims in that darkness, whether anything has ever grown in that dark warmth, whether the atoms of carbon and nitrogen and oxygen dissolved in that water have ever arranged themselves into something that replicates. We do not know. We did not know the ocean was there at all 30 years ago. Now we know it is there. Now we know what it contains. Now we know that a spacecraft can fly through its erupted material and taste it, and that the taste is compatible with life. That is not a small change in what we know. That is a transformation of the question. It is the difference between asking whether there is anyone home and knowing that the house is heated, and the kitchen is stocked and the lights are on. Someone will go and knock on the door, eventually. We are patient as a species when we have to be, and we know because Cassini told us that the door is worth finding, the signal is gone, the science isn't. What we are left with, in the silence after that last green spike disappeared from the monitor, is not an absence. It is a direction, a specific, measured, chemically characterized direction into the darkness toward a small erupting moon orbiting a planet whose rings will outlast us, though not by as much as we once thought. The universe did not give us certainty at Saturn. It gave us coordinates. The next question has already been written in the data. It just needs someone younger, with instruments we haven't built yet, pointing a spacecraft we haven't designed yet at a precise location we know exactly, to go and ask it.